Welcome to Med Together. This is a podcast by the people, for the people, as it were. My name is Chana. I'm a med student in New York. This podcast deals with a lot of med school topics, starting from the basic sciences and building its way up, and hopefully it'll be a bit of review that can help y'all consolidate and synthesize important information and maybe phrase it in a way that's easy to understand. By the way, if you're pre-med or you're a nursing student, or you're just interested in sciencey, medically topics, and you're not in healthcare at all, you're totally welcome to. We don't discriminate. If you're interested, you're cool. Ready to rock? Let's do this. Hey everyone, welcome if you're new, welcome back if you're a repeat listener. In this episode, we're going to talk about cholesterol synthesis and the consequences thereof, and then we'll do a wrap up to try to put this whole lipid picture together, because I know we've kind of done it in pieces, so I want to put the puzzle back together and try to give you sort of an overall feel for how this whole flow works. So why are we even talking about cholesterol? Why is cholesterol important? Cholesterol is super important in membranes, actually, because it helps to determine their biophysical properties. Cholesterol is a very unusual lipid because it has no large polar head group. It's entirely nonpolar except for one hydroxyl group, so it nestles in the membrane. And the cholesterol actually organizes the lipids in the membrane into structures which can affect signal transduction. So for this reason, levels of cholesterol in cells are going to be very highly regulated. Now, every nucleated cell can make cholesterol, but it's very precisely regulated because, like we said, it has such an importance in membrane properties. Now, the endoplasmic reticulum is really the signaling center for cholesterol in the cell, and the level is held very tightly at about 5%, whereas the plasma membrane tends to live at about 35 to 40% cholesterol. Cholesterol can move around the cell between organelles by transporters, but it can't move by itself because it's very water insoluble, so it always kind of has to be carried if it wants to go somewhere. Now, if we think about cholesterol at a sort of whole body level, we get rid of about half a gram of cholesterol per day, and we'll talk about how we get rid of it, and we replace it through diet and synthesis. Synthesis is very highly regulated to keep the cholesterol in range, but unfortunately, our bodies cannot on their own regulate our intake. So high fat and high cholesterol diets that we tend to eat are really outside the regulatory range, and this is why we end up with these major killers of heart disease and stroke from cholesterol buildup. It's because we're eating outside of the range that our bodies can regulate. So let's talk about cholesterol synthesis, and I'm going to talk about it by saying I'm not talking about it. What I mean by that is it's a really long pathway. I think there are 22 steps, but we're not going to go through every step of it because it's really not important right now. The things that I want to tell you are this. It occurs in the cytoplasm. The precursor is acetyl-CoA. Remember, acetyl-CoA is always going to be super important in all of lipid metabolism. And the key regulatory step in synthesis is mediated by an enzyme called HMG-CoA reductase, which makes mevalonate. And this is the enzyme that's inhibited by statins, which are competitive inhibitors that work by blocking the active site of the enzyme. And statins are the major cholesterol-lowering drug that we use. So once cholesterol is synthesized, it actually goes to the endoplasmic reticulum and it gets esterified. This esterification in the endoplasmic reticulum is reversible. So cells store cholesterol esters and then they hydrolyze them to regenerate cholesterol as needed. Now, how do cells do cholesterol uptake from, let's say, dietary cholesterol or cholesterol that's formed in another cell? So this happens via the LDL receptor. LDL stands for low-density lipoprotein, which is how cholesterol is mostly packaged. And this receptor binds LDL, and then it gets internalized in a clathrin-coated pit, which kind of pinches off the membrane and becomes what we call a sorting endosome. The LDL receptor then dissociates from the LDL in the sorting endosome. The receptor gets recycled, and the LDL goes to hydrolytic lysosomes, which then remove the ester and gives free cholesterol, which is shepherded by NPC1 and NPC2 to be transported to places in the cell that it's needed. Let's refresh again what a lipoprotein actually is. So lipoprotein is a storage molecule for fats. The core of a lipoprotein is triacylglyceride and cholesterol esters, and the shell is a monolayer of lipids. Remember, this is not a lipid bilayer because if we remember back to when we formed these, this was a pinching off of just the cytoplasmic leaflet of the endoplasmic reticulum. So it's just a monolayer of lipids, and there's also unesterified cholesterol. And then the lipoproteins that are made in the liver carry apoproteins on them. So some of the apoproteins are very tightly associated. The ApoB48 on chylomicrons made in the intestines and ApoB100 on lipoproteins made in the liver are tightly associated, while ApoE and ApoC2 can hop on and off in the circulation as they're needed. There are four main types of lipoproteins, and in order of size from least to greatest, so smallest to largest, that's going to be HDL, high-density lipoprotein, LDL, low-density lipoprotein, VLDL, very low-density lipoprotein, and chylomicrons. And the biggest differences in composition is that the core of LDL is mostly cholesterol esters versus in VLDL and chylomicrons, it's going to be mostly triglycerides. And when we talk about lipoprotein trafficking, let's just remind ourselves that all roads lead to the liver. The liver is the central organ of a lot of things, but it also happens to be the central organ of cholesterol metabolism. So ApoB48 carrying chylomicrons are formed in the endoplasmic reticulum of intestines, secreted to the lymphatics, and then they go to the blood. In the blood, they're going to pick up ApoE and ApoC2. ApoC2 activates lipoprotein lipase in adipose and muscle, which hydrolyzes the triglycerides in the chylomicron and leaves what we call a chylomicron remnant. The ApoE then binds and gets the remnant endocytosed into the liver, and it follows an LDL similar pathway in the liver. So it goes from a sorting endosome to a lysosome, etc. So now the liver is going to have lots of fatty acids and cholesterol, which it processes into VLDL, a very low density lipoprotein, with ApoB100, and it sends it out to the circulation. As it circulates, it's going to pick up that same ApoC2 and ApoE. It's going to deliver triglycerides to the cells that need it so that it gets down to be smaller, and eventually it's going to have mostly cholesterol left. And when it has mostly cholesterol left and it's smaller, it becomes LDL. And now it's going to be small enough to get into other tissues where it can be picked up by LDL receptor endocytosis in other tissues, because remember, all cells need cholesterol. And you'll get hydrolysis in the cell that took it up and cholesterol redistribution within that cell. Two things to mention here. PCSK9 is an important one. PCSK9 binds competitively to LDL receptors in the liver cells, and it causes degradation of LDL receptors because it gets endocytosed into the sorting endosome, but since it's not real LDL, it doesn't dissociate from the receptors, so it causes the receptors not to be recycled and instead to be destroyed by the lysosomes. So this reduces the number of LDL receptors on the liver surface, and even though the liver can make more receptors, it can't usually keep up with the PCSK9. So LDL starts to build up in circulation. And interestingly, this was discovered kind of backwards. This was discovered in people with super low LDL because they had loss of function mutations in PCSK9. PCSK9 is something that we all have. Some of us have more, some of us have less, and we'll come back to PCSK9 when we talk about familial hypercholesterolemia. But this was discovered through people who had loss of function mutations in PCSK9, so their LDL receptors were working better because none of them were getting destroyed, and they had super low LDL. There's a mutation called the JD mutation, also to just be aware of, which is a mutation that leads to super high cholesterol levels because receptors are unable to get clustered into those clathrin pits that's needed for endocytosis. So they can't be endocytosed, so circulating cholesterol is going to be super high because none of the cells can take up pretty much any cholesterol from LDL. Now we have to talk about reverse cholesterol transport. What in the world is reverse cholesterol transport? So this is basically when there's return of extra cholesterol to the liver from peripheral tissues, and this is mediated by HDL, which is the one lipoprotein we didn't really talk about yet, because we talked about chylomicrons made by the intestines, we talked about how the liver makes VLDL, and then it loses its triacylglycerides, it becomes LDL, and then it gets taken up by lots of different cells. So now we have to talk about the fourth one, which is HDL. So a nascent HDL particle is like a disc. It's lots of phospholipids with a little bit of cholesterol in between, and it's just pretty much flat. It carries the protein ApoA1 on it, and it kind of floats around in the blood, and it accepts cholesterol from cells like macrophages to transport back to the liver. And in the circulation, the cholesterol inside the HDL immediately gets esterified, which allows it to maintain a cholesterol gradient that continues to take up cholesterol because the esterified cholesterol doesn't count for the gradient. So it gets esterified, and then it's as if there's nothing inside the HDL, and it can continue taking up cholesterol. And as it quote-unquote eats the cholesterol, it goes from a disc to a dense sphere, hence the name high-density lipoprotein. And the HDL can then be recognized by the liver. The liver takes it up, it takes the cholesterol esters out, and it can make bile acids with it, it can do other things with it, but basically it cleans up the extra cholesterol that's hanging out in the blood and in other cells. What are bile acids? These are the main way that we get rid of cholesterol, actually. This is remember I said we lose 0.5 gram of cholesterol per day? Basically, it's in bile acids. So bile acids are produced in hepatocytes. They're secreted to the duodenum where they function as emulsifiers, basically like detergents that help dissolve dietary fats. And actually most of our bile acids are recycled. They're returned to the liver for reuse, but the about 5% that's not recycled is how you get rid of some cholesterol. And I'm going to make this point again. I made it before, but it's kind of a soapbox for me. This is why we should not be eating so much cholesterol, because think about how very little we get rid of per day. Really so little, and we take in so much cholesterol, and this is how we get ourselves into this huge mess that is the heart disease epidemic in America. and the rest of the world, frankly. But I say America because that's where I'm going to medical school and that's what gets emphasized in our school. But this is what's causing, to a large degree, this huge health crisis, is the fact that we just are eating too much cholesterol and our bodies can't handle it. Okay, sorry. I'll get off my soapbox now and discuss with you how the endoplasmic reticulum does regulation of cholesterol. So there is a protein called SREBP, sterile regulatory element binding protein. The great thing about biologists is that they're really good at naming things by exactly what they do. So if you can remember what all the letters mean, you know exactly what it does. And what it does is it's a transcriptional regulator, which is normally a membrane-bound protein associated with SCAP, which, get this, stands for SREBP, cleavage-associated protein. I know these names are great. They're associated together in the endoplasmic reticulum. And when cholesterol is high, SCAP is bound to SREBP, and it's also bound to INSIG, and it's held inside the endoplasmic reticulum. But when cholesterol is low, and this is sensed by the endoplasmic reticulum, INSIG dissociates, and SCAP and SREBP get packaged and sent to the Golgi together. The SCAP is necessary to stabilize and shepherd the SREBP into the right place in the Golgi, and then its job is over. The SREBP in the Golgi undergoes two cleavages, which releases the N-terminus, and the N-terminus is the actual regulatory part. And so this N-terminus gets sent to the nucleus to regulate transcription of synthetic pathways of cholesterol and the LDL receptors. Now, this threshold for high and low cholesterol is very, very subtle. So that makes for super, super tight regulation. Like when I say that the cholesterol is low, I mean like if you were looking at it, you would never detect that it was low. But the ER is super, super sensitive and regulates it very tightly. Now, aside from the fact that cholesterol is needed for membranes, which is super important, another thing that we use cholesterol for is that it's actually the precursor for all steroids, which are made in the mitochondria of steroidogenic cells. So another reason why cholesterol and having cholesterol in the correct proportion is important to us. And I want to mention, I know we said we weren't going to talk about the synthetic steps of cholesterol, and we're not, but I want to mention isoprenes, which are an intermediate step in the cholesterol synthesis pathway. And I'll tell you why. So aside from being used as membrane anchors, which they are, isoprenes are also precursors for CoQ10, which, if you remember, CoQ10 is an electron carrier. And they're also precursors for certain vitamins. So for this reason, you may see patients who take a CoQ supplement together with statins, because if you stop the cholesterol synthesis pathway, you're also not producing isoprenes. You can get a CoQ deficiency. So a lot of people will take a CoQ supplement along with their statin. All right. Now let's talk about atherosclerosis, which is the whole reason that cholesterol has been made into this evil, evil thing, which it's not really. We need it. We just have too much of it and we get this atherosclerosis. So how does this happen? Like we said, low density lipoproteins are small enough to slip between cells, but the problem is that they can slip between endothelial cells and you start to get a buildup of LDL inside the wall of a blood vessel. So what happens when you have a buildup of trash? You get the cleanup guys. Monocytes go in to clean up the mess. They differentiate into macrophages there in the wall of the endothelial cell to try to endocytose the LDL. The problem is that that amount of cholesterol is toxic to the macrophage. So it gets so full of cholesterol that it's called a foam cell. And then this foam cell gets an endoplasmic reticulum stress reaction that leads to apoptosis of the macrophage. So now you have dead macrophage plus all this cholesterol junk. So what happens? Another macrophage comes along to clean it up. Then the same problem just repeats itself. It eats the lethal amount of cholesterol. It dies as well. You get buildup of dead macrophages along with buildup of cholesterol, and it turns into this really, really ugly mess. This buildup leads to narrowing of the arteries. And so you can have this chronic problem, chronic narrowing of the arteries, but also you can acutely get a breakage in the vessel wall. And then a clot is going to form over that to try to stop bleeding. And this can block the narrowed vessel completely, leading to an acute myocardial infarction, which we colloquially call a heart attack. Now, normally, how do we get hypercholesterolemia? High cholesterol is, like I said, a long life of eating too much cholesterol, pretty much. We eat too much and our bodies can't balance it out. But there is a condition called familial hypercholesterolemia, which I want to talk about a little bit. I'm not going to go into too much huge detail, but it is kind of important because it's something to think about when you see elevated cholesterol. So there's two different forms. There's a heterozygous form and a homozygous form. The heterozygous form is inherited in an autosomal dominant fashion. It's more commonly seen in French Canadians and Dutch Afrikaners, and the prevalence of this heterozygous form is 1 per 200 or 250 patients when the LDL is above 190. So this is not 1 per 250 patients in general. This is if their LDL, which you measure by a blood test, is above 190, 1 in 200 or 250 of these patients may have this heterozygous form of familial hypercholesterolemia. The homozygous form is more rare, and in this form, they may have 2 of the same mutation, or they might have 2 different mutations altogether. And we'll talk a little bit about the kinds of mutations that can cause hypercholesterolemia. But just to remind you, so homozygous, even though homozygous generally means 2 of the same, what we mean by homozygous is we mean they have problems in both copies of their gene, but they're not necessarily the same problem. So they're actually technically not a homozygote. They're technically a compound heterozygote, but that's not what it's called. We call it a homozygous form. So that's just what I'm going to go with. And this one, like I said, is a little bit more rare. So for this one, the LDL is going to be really high. So if the LDL range is above 500 milligrams per deciliter, it's still only going to be 1 in 300,000. So even in a super high LDL, having someone who's homozygous for familial hypercholesterolemia is pretty rare, which makes sense. Homozygotes in general are more rare than heterozygotes because there's so much chance involved in getting 2 defective alleles, right? Some things that might tip you off are on physical exam, you can find things like xanthomas or xanthelasmas, which are like skin tags, which are actually just cholesterol deposits. And you can find them on extensor surfaces like knuckles or elbows, and sometimes you see them around the eyes also. Another thing, which is maybe like an exam buzzword, so maybe kind of keep it in the back of your head, is corneal arcus. These are white rings around the iris, and these are abnormal in young patients. In patients older than 45, you may see these even in patients who don't have this condition, but if you see these in a young patient, it should definitely raise red flags for familial hypercholesterolemia. So let's talk about some of the common mutations that may cause familial hypercholesterolemia. And the most common mutations are going to be mutations in the LDL receptor of the liver. So the liver can't take up cholesterol properly, too much cholesterol accumulates in the blood. And there are many, many different kinds of mutations that can occur in the LDL receptor. But most commonly, it's going to be an LDL receptor mutation. We can also sometimes see mutations in ApoB, which, remember, are the proteins that sit on the outside of the lipoprotein. And so if there are mutations in ApoB, there's trouble with packaging of the cholesterol, so it can't get taken up properly by other cells because they don't have the right signals that tell them to take it up. Another mutation that you can sometimes have is gain of function in PCSK9. So if you remember, we talked about PCSK9 was actually discovered through loss of function mutations, and these people had super low cholesterol. But a gain of function mutation in PCSK9 would lead to a lot of destruction of LDL receptors. You can't take up as much LDL and you end up with more cholesterol in the blood. Now, it's really important to consider screening for this condition and screening for cholesterol. So cholesterol screening should be started in pediatric patients. You should always screen just once. So for adults, we want to be checking cholesterol at every well visit. This is not the case for pediatric patients, but every pediatric patient should be screened. Just do it once, check the LDL levels, especially if there's a family history. And the reason why it's so important to screen and to catch early is because not all high LDL levels are equal. So the time of exposure to LDL is what increases the risk of heart disease. So prolonged exposure to high levels of LDL is really the problem. So if we detect these earlier and we can treat earlier, try to lower the LDL very aggressively earlier in life, this greatly improves their chances of not getting heart disease. And if we don't do this, and we do leave people with this increased LDL exposure, we commonly, in homozygous familial hypercholesterolemia, we commonly see aortic stenosis, which is calcification of the aortic valve. We see premature atherosclerotic disease. It tends to be in coronary arteries, but it can be found in the carotid artery, renal arteries, peripheral vasculature. And people with homozygous familial hypercholesterolemia can get this really young, like in their 20s and 30s. Whereas heterozygotes tend to develop it a little bit later, like in their 40s and 50s. But still, that's very, very young. And knowing that if we screen younger, we can treat this aggressively and hopefully hold off these really terrible complications is one of the reasons I really wanted to bring this up, because this is not something you may see commonly, but it's something that is kind of preventable if we screen properly, and it's such an easy blood test. So how do we treat these? We treat them with, like I said, aggressive lowering of cholesterol. One of the most common things we do is statins. These are the most common drugs for cholesterol lowering. They block cholesterol synthesis, which also is going to upregulate LDL receptors because the cell is like, oh no, I don't have enough cholesterol. So even at the lowest dosage, you can get a 30% reduction in LDL using these. Side effects include muscle aches, liver enzyme elevation, but these are not usually serious and they're usually fairly manageable. There's another drug called ezetimibe, which blocks intestinal absorption of cholesterol. And in response, the liver is again going to upregulate LDL receptors. These can be synergistic with statins. They're often used together. These are not as commonly used. Like, you're not going to see these prescribed in the gen pop as much as you see statins, but they're fairly useful as kind of an adjuvant therapy. Bempedoic acid is another one which blocks conversion of acetyl-CoA to citrate in the cholesterol synthesis pathway. So it works similarly to statins, but it uses a different pathway, and this one has lower risk of muscle ache side effects. Specifically, if there is a PCSK9 mutation, we can use PCSK9 inhibitors, which are monoclonal antibodies. This is a biweekly injection that blocks PCSK9. And then there are sort of the more further down the line things. We can do apheresis, which is similar to dialysis, where the blood is filtered externally. This is tough. It has to happen weekly or every 2 weeks, and there's a huge acute drop in cholesterol, but then it does rebound, so you have to keep doing it. And currently this treatment is only approved for people who are homozygous or for people who are heterozygous with LDL greater than 100 and known vascular disease. So they have a lot of risks, and you really have to lower their LDL really fast. But this is tough, and it's inconvenient, and it's not curative. It's just kind of holding things off. And then a liver transplant. This is a kind of a last-ditch effort, a sort of a Hail Mary, is to get a new liver. This is the center for processing and production, so getting a new one could help. But one of the biggest problems with this is that liver transplant, we actually often can get living donors. But usually, when we get a living donor for a liver transplant, the best candidates are family members because it's a fairly easy surgery. There's not a huge amount of risk to the donor, and most family members are willing to give up a piece of their liver. The problem in these kind of conditions is that family members are not usually good candidates because they may also have mutations. So they may have to go on the actual liver transplant list, which they could be on for a long time. There is a shorter waiting list for pediatric patients, so sometimes if we catch this really young, especially in a kid who's homozygous, we might consider trying to put them on the transplant list fairly early, but this one's a toughie. Okay, so that was cholesterol and familial hypercholesterolemia, which I feel like was just an important thing to spotlight. And now I'm going to do what I said I was going to do before, which is sort of the wrap up of everything we've talked about last episode and this episode, trying to see the lipid metabolism process from start to finish as much as you can, because it's not a linear process, obviously. So I'm going to start kind of at what I felt was the logical beginning, which is what happens when you eat fat. So triacylglycerides, which are fatty acids bound to a molecule of glycerol from our diets, are emulsified by bile acids and broken down by gastric lipases to yield free fatty acids, which can be taken up by intestinal cells. The free fatty acids get trafficked to the endoplasmic reticulum, where they're repackaged into triacylglycerides. This synthesis occurs in the membrane of the endoplasmic reticulum between the two leaflets. As the pool of triacylglycerides grows, it forms a bulge in the membrane of the ER that eventually buds off into what is known as a lipoprotein, or a chylomicron, composed of a core of mostly triacylglycerides with some cholesterol. We do take up some dietary cholesterol, which gets moved through this same process, just most of what we eat is triacylglycerides. And this core of lipids is going to steal the cytoplasmic leaflet of the endoplasmic reticulum to be its monolayer coat of phospholipids. Lipoproteins made in the ER of the intestinal cells have a surface protein called ApoB48, and they're called chylomicrons. The chylomicrons are secreted from the basal side of the intestinal cells to the lymph, and eventually to the bloodstream. They have to acquire some more apoproteins along the way, ApoE and ApoC2, neither of which is intrinsic, but they just kind of hop on and off as needed. When the chylomicrons get to adipocytes, the ApoC2 stimulates action of lipoprotein lipase, which can get into the chylomicron, break up the triacylglycerides back into free fatty acids, which it then gives to the adipose tissue and to other tissues. The remnant of the chylomicron gets taken up by the liver in an ApoE-mediated process. Now, the liver has to deal with the delivery of fatty acids and cholesterol, which it does by creating VLDL, very low-density lipoprotein, and we'll get back to talking about what happens with VLDL when we come to cholesterol. But for now, let's take a break and talk about what happens when blood glucose is low. So glucagon is going to signal through a GPCR, and using cyclic AMP turns on PKA, protein kinase A, which phosphorylates and stimulates lipases in the adipocytes to break up the triacylglycerides that they were storing, and send the components, the free fatty acids and the glycerol, to the liver, where the free fatty acids will be oxidized for energy and the glycerol can be used for gluconeogenesis. When the fatty acids arrive at the liver, they need a transporter to get across the membrane, and then similar to what happens with glucose, they get conjugated to CoA to trap them inside the cell. Now, beta oxidation takes place in the mitochondria, and the acyl CoA can't cross in alone, so they need to get uncoupled from CoA and attached to carnitine, which has a transporter and can shuttle them across. Once in the mitochondria, they hop off carnitine back onto CoA. The acyl CoA undergoes a series of oxidations, losing a pair of carbons at a time, where one NADH and one FADH2 is produced for every pair of carbons that gets chopped off. At the end, we're left with either acetyl-CoA, the buildup of which drives pyruvate carboxylase and gluconeogenesis, or if this was an odd-chain fatty acid from the diet, we'll be left with propionyl-CoA, which gets converted to succinyl-CoA with vitamin B12. If we continue to build up acetyl-CoA to a large degree, and the blood glucose is still not where it should be, the liver has another trick up its sleeve. It can't convert all this acetyl-CoA back to glucose, but using HMG-CoA reductase in the mitochondria, it will convert it to ketone bodies, hydroxybutyrate and acetone, which it sends out into the bloodstream. The reason it sends it all out is because the liver itself can't do anything with these ketone bodies, but the brain and other tissues can convert it back to acetyl-CoA, feed it into their TCA cycles as a knockoff glucose. Nobody's going to be very happy about it, but it will keep the brain alive, which is what counts for now. Now, what about after a high-carb meal where there's lots of glucose in the cell? Well, the liver first does its usual thing. It makes glycogen, it diverts glucose into the pentose phosphate pathway, all that good stuff. But when those pathways are saturated and the glucose is still coming, the liver is going to turn the extra carbons into cholesterol and fatty acids, and eventually triglycerides for storage. Let's talk about fatty acids first because they're easier. Fatty acids are synthesized in the cytoplasm and require carboxylation of acetyl-CoA into malonyl-CoA. This process is turned on by insulin, which tells the body to be in an anabolic state. Malonyl-CoA is also going to inhibit the carnitine shuttle so that the newly made fatty acids don't just get taken into the mitochondria and broken down. You might ask, wait, how do we have acetyl-CoA in the cytoplasm? I thought it's made in the mitochondria. This is an excellent question. The acetyl-CoA in the cytoplasm comes from the breakdown of citrate. When there's lots of glucose and the TCA cycle is being allosterically inhibited by high levels of ATP, the citrate can get bled off and come into the cytoplasm. Then citrate lyase will break it back down into its components, which are acetyl-CoA and oxaloacetate, giving you free acetyl-CoA in the cytoplasm. Now, there is an energy pay-in to this process of fatty acid synthesis. It takes energy to make energy. That's a general rule. But basically, 2 carbons are added at a time to create a fatty acid chain, which is why humans only make even fatty acid chains, because we add 2 at a time. And sometimes an additional enzyme will come in and make some double bonds. The fatty acids then get trafficked to the endoplasmic reticulum, where triacylglycerides are made, by activating the fatty acids with ATP and then attaching it to a glycerol phosphate backbone. This will give you a phospholipid. If you want to go all the way, you can remove the phosphate and add another acyl chain in a separate step and make a triacylglyceride. They then get packaged into lipoproteins together with cholesterol, and I'm going to take a second to talk about cholesterol synthesis now because it's part of the process. So in high energy states, cholesterol can be synthesized in the cytoplasm. We didn't talk much about the synthesis process except to say that it uses HMG-CoA reductase, which is kept separate from the mitochondrial version, which is used to make ketone bodies under opposite circumstances, so we don't want those enzymes to mix. And it turns acetyl-CoA into mevalonate. This is the key regulatory step. Now, cholesterol synthesis is actually tightly regulated by the cholesterol levels in the ER, more so than the amount of glucose in the cell. The SRABP pathway has a transcriptional regulator, which is normally an ER membrane protein. When the cholesterol is high or normal, it's bound and kept inside the ER. When the cholesterol is low, it gets sent to the Golgi body, cleaved, signals to the nucleus, and induces transcription of biosynthetic pathways of cholesterol and of LDL receptors. Remember again that the threshold for high and low cholesterol is very subtle, so this regulation is very tight. Okay, so now back to where we were. The triacylglycerides that were synthesized in the liver ER, as well as some cholesterol, get packaged into lipoproteins similar to what happens in the intestinal process, but these are called VLDL. Very low density lipoproteins, and they carry an intrinsic ApoB100 as well as the more transient ApoE and ApoC2. This is the same thing that happens to the cholesterol and triacylglyceride received by the liver in the chylomicron remnant. So whether it's freshly synthesized triacylglycerides and cholesterol or whether it's received from chylomicron remnants, the liver does the same thing. It makes VLDL. These very low density lipoproteins then get sent out to the blood, and ApoC2 activates lipoprotein lipase. It delivers triacylglycerides to the adipocytes for storage or to cells that need fatty acids, similar to what happens to the chylomicrons. At this point, there's mostly only cholesterol left inside, and now it becomes known as LDL, low density lipoprotein, and it's small enough to get into all the tissues and deliver cholesterol. Every cell needs cholesterol, remember, because it's important for membrane stability and signaling, etc. How does LDL get into the cells? LDL binds to LDL receptors. It undergoes clathrin-mediated endocytosis. In the sorting endosome, the LDL receptor gets recycled and the cholesterol gets distributed within the cell to wherever it needs to go. Sometimes, though, this sneaky ability of LDL to get between tissues is not such a good thing because you start to get a buildup of it under the endothelial cells that make up blood vessels. When macrophages go to clear up the blockage, they start to phagocytose the LDL, but they're literally biting off more than they can chew, and the level of cholesterol turns them into foam cells and kills them. Now more macrophages come to clean up, they ingest toxic levels of cholesterol, turn into foam cells and die, and it's a really nasty cycle. And this buildup of dead cells is called atherosclerotic plaque and causes narrowing of the arteries, raising the blood pressure. An acute MI will occur when there's a rupture in the wall of the vessel, and the body creates a fibrothrombin plug to close the break, but the artery is so narrow that the blood flow gets completely occluded. So that's LDL, which we also sometimes call bad cholesterol. And now what about the good cholesterol, the HDL? So HDL helps with reverse cholesterol trafficking back to the liver. A nascent HDL particle is like a disc. It has lots of phospholipids with just a little bit of cholesterol, and it accepts cholesterol from cells such as macrophages to transport back to the liver. In the circulation, the cholesterol inside the HDL gets esterified, which makes it go from a disc to a sphere, and it allows the HDL to keep accepting cholesterol because it's creating a gradient where free cholesterol is low inside the HDL. The HDL can then be recognized by the liver will take the cholesterol esters out and can make bile acids, which is the main way we get rid of cholesterol and other things. Okay, I believe that wraps up our conversation about lipid metabolism. I hope this was useful and you learned something today, and I'll catch you in the next episode.